Gauss's law. Electric flux. Electric flux is the amount of electric field going across a surface. It is defined in terms of a direction, or normal unit vector, perpendicular to the surface. For a constant electric field, and a flat surface, it is easy to calculate, denoted by E. Units of an m2/c. When the surface is flat, and the fields are constant, you can just use multiplication to get the flux. When the surface is curved, or the fields are not constant, you have to perform an integration. Electric flux for a cylinder. A point charge Q is at the center of a cylinder of radius a and height 2b. What is the electric flux out of A, each end, and B, the lateral surface? Top S B B R R Z. Consider a ring of radius s and thickness ds. A Q B A. Lateral surface. Total flux out of various shapes. A point charge Q is at the center of A, sphere, B, joint hemispheres, C, cylinder, D, cube. What is the total electric flux out of the shape? B A Q Q A Q. Gauss's law. No matter what shape you use, the total electric flux out of a region containing a point charge Q is 4 keq equals Q/0. Why is this true? Electric flux is just measuring how many field lines come out of a given region. No matter how you distort the shape, the field lines come out somewhere. If you have multiple charges inside the region, their effects add. However, charges outside the region do not contribute. Q, Q4, Q3, Q1, Q2. Using Gauss's law. Gauss's law can be used to solve three types of problems. Finding the total charge in a region when you know the electric field outside that region. Finding the total flux out of a region when the charge is known. It can also be used to find the flux out of one side in symmetrical problems. In such cases, you must first argue from symmetry that the flux is identical through each side. Finding the electrical field in highly symmetrical situations. One must first use reason to find the direction of the electric field everywhere. Then draw a Gaussian surface over which the electric field is constant. Use this surface to find the electric field using Gauss's law. Works generally only for spherical, cylindrical, or planar type problems. Sample problem. The very long box has the shape of a regular pentagonal prism. Inscribed in the box is a sphere of radius r with surface charge density. What is the electric flux out of one lateral side of the box? End view. Perspective view. The flux out of the end caps is negligible. Because it is a regular pentagon, the flux from the other 5 sides must be the same. Using Gauss's law to find E field. A sphere of radius a has uniform charge density throughout. What is the direction and magnitude of the electric field everywhere? Clearly, all directions are created equal in this problem. Certainly the electric field will point away from the sphere at all points. The electric field must depend only on the distance. Draw a sphere of radius r around this charge. Now use Gauss's law with this sphere. R A. Note, we implicitly assumed r greater than a when we calculated the enclosed charge. Using Gauss's law to find E field, 2. A sphere of radius a has uniform charge density throughout. What is the direction and magnitude of the electric field everywhere? When computing the flux for a Gaussian surface, only include the electric charges inside the surface. R A. Electric field from a line charge. What is the electric field from an infinite line with linear charge density? L R. Electric field must point away from the line charge, and depends only on distance. Add a cylindrical Gaussian surface with radius r and length L. Use Gauss's law. The ends of the cylinder don't contribute. On the sides, the electric field and the normal are parallel. Electric field from a plane charge. What is the electric field from an infinite plane with surface charge density ? Electric field must point away from the surface, and depends only on distance d from the surface. Add a box-shaped Gaussian surface of size 2 dLW. Use Gauss's law. The sides don't contribute. On the top and bottom, the electric field and the normal are parallel, conductors and Gauss's law. Conductors are materials where charges are free to flow in response to electric forces. The charges flow until the electric field is neutralized in a conductor. Inside a conductor, E equals 0. Draw any Gaussian surface inside the conductor. In the interior of a conductor, there is no charge. The charge all flows to the surface. Electric field is surface of a conductor. Because charge accumulates on the surface of a conductor, there can be electric field just outside the conductor. Will be perpendicular to surface. We can calculate it from Gauss's law. Draw a small box that slightly penetrates the surface. The lateral sides are small and have no flux through them. The bottom side is inside the conductor and has no electric field. The top side is area A and has flux through it. The charge inside the box is due to the surface charge. We can use Gauss's law to relate these. Sample problem. An infinitely long hollow neutral conducting cylinder has inner radius A and outer radius B. Along its axis is an infinite line charge with linear charge density. Find the electric field everywhere. B. End-on view. Perspective view. A. Use cylindrical Gaussian surfaces when needed in each region. For the innermost region, R less than A, the total charge comes entirely from the line charge. The computation is identical to before. For the region inside the conductor, the electric field is always 0. For the region outside the conductor, R greater than B, the electric field can be calculated like before. The conductor, since it is neutral, doesn't contribute. Where does the charge go? How can the electric field appear, then disappear, then reappear? Plus. Dash A. Plus. The positive charge at the center attracts negative charges from the conductor, which move towards it. This leaves behind positive charges, which repel each other and migrate to the surface. End-on view. In general, a hollow conductor masks the distribution of the charge inside it, only remembering the total charge. Consider a sphere with an irregular cavity in it. Plus. Cutaway view. Dash A. Q.